In vision and language navigation, an AI agent must follow natural language instructions like go to the pot in the kitchen and navigate through a 3D environment using only visual input and textual feedback. This task sounds simple, but in practice, even state-of-the-art models struggle. Why? Because these agents don't just need to see, they need to understand. And when they fail, it's not always because of poor planning. Often it's because of hallucinations. The agent thinks it sees a target that isn't there, or misses one that's clearly in view. It might misinterpret spatial relationships, believing the target is on its right when it's actually on the left. Or worse, it generates invalid actions, like walking into a wall. These are not minor bugs. They're systemic failures rooted in how large vision language models, or LVLMs, process visual information, especially in continuous, real-time navigation tasks. Today, we dive into a groundbreaking new framework called SeeNav-Agent, developed at Tencent AI Lab, which tackles these issues head-on. It introduces two key innovations: a dual-view visual prompt system to reduce perception errors, and a novel reinforcement fine-tuning algorithm called Step Reward Group Policy Optimization, or SRGPO, that dramatically improves reasoning and planning. Let's start with the problem, perception. Most VLN agents rely on a single input, usually the front view or first-person perspective. But this view lacks depth cues. Objects appear flat. Spatial relationships are ambiguous. Meanwhile, bird's-eye views or top-down views show depth and layout, but they distort object shapes. A pot might look like a rectangle, not a cylinder. So even if the agent sees the right shape, it might fail to recognize it. That's where dual-view input comes in. SeeNav-Agent combines both the front view and the bird's-eye view, side by side, and feeds them into the model as a single image. But raw dual-view input isn't enough. Without guidance, the agent gets confused. It can't align the two perspectives or understand how they relate. So the team designed a visual prompt system, a set of carefully crafted annotations that guide the model's attention. First, bounding boxes. A red box is drawn around the target object in both views. This tells the model, this is what you're looking for, no more guessing. Second, navigation lines, red arrows pointing from the agent to the target in both views. These aren't just decorative. They give the agent a clear sense of direction and distance. If the arrow is long, the target is far. If it's short, it's close. And if the arrow disappears from the front view, that means the target is out of sight. Third, agent markers. In the top-down view, the agent is represented as a circle with a green arrow showing its orientation. The left side is yellow, the right is purple, a simple but powerful cue to prevent left-right confusion. Because yes, even AI can get turned around. Fourth, action projection. Every possible action, move forward, turn left, tilt up, is drawn on the image. Movement actions appear as blue arrows in the top-down view. Rotations appear in the front view. Each action is labeled with an ID. This turns the navigation task into a visual question-answering problem. Which arrow represents the best next step? And fifth, view alignment. Here's a subtle but crucial fix. In the top-down view, the agent's orientation is random. But that creates confusion. If the agent is facing down in the top-down view, left and right are flipped. So SeeNav-Agent dynamically rotates the bird's-eye view to match the agent's orientation, so it always faces forward. Now left is left, right is right, and the agent never gets disoriented. Together, these visual prompts form a zero-shot recipe, no training needed. Just add the prompts, and the agent's perception improves immediately. And the results? Stunning. When GPT-4.1 is paired with this dual-view visual prompt system, its navigation success rate jumps to 86.7%, a massive 20 percentage point improvement over the previous best closed-source model. That's not a small win. That's a leap. But perception is only half the battle. Even if the agent sees correctly, it still has to reason and plan. And here's where traditional reinforcement learning falls short. Most agents are trained using outcome rewards, a binary signal, success or failure. But in long navigation tasks, that's like giving a student a final grade without feedback on individual steps. You can't learn from mistakes when you do know which step went wrong. Some approaches try to fix this with step-level rewards, rewarding each action based on whether it brings the agent closer to the goal. But existing methods like SRGPO require grouping steps that are identical in state, meaning the agent must be in the same position, with the same view, to compare actions. That's incredibly restrictive. It requires rolling out dozens of trajectories just to find enough matching states. Computationally expensive, slow, and fragile. SeeNav-Agent solves this with SRGPO, Step Reward Group Policy Optimization. The key insight: design a verifiable process, reward that's independent of the state. How? By defining a reward based purely on two things. 1. Did the agent get closer to the target? 2. Did the target come back into view after being lost? That's it. No need to know the environment. No need to match states. The reward is based on objective, measurable changes, distance, and visibility. This reward is called VPR, or Verifiable Process Reward. And because it's state-independent, we can now group steps randomly, not by state but by time. In a batch of 4 trajectories, each with 20 steps, we can randomly sample 16 steps from anywhere across the batch and form a group. Then compute the average reward within that group, and use that to estimate advantage. No more strict state matching. No more massive rollout overhead. Just efficient, dense reward signals at every step. And the results? SRGPO converges faster, trains more stably, and generalizes better than GRPO or GGPO. On the QN2, 5VL3B model, SRGPO achieves a success rate of 72.3%, 5.6 percentage points higher than the previous best open-source model. And it beats GGPO by 14.5 pp on test scenarios, proving it's not just good at training, it's good at generalizing. But what about training stability? Let's look at the curves. With SRGPO, the success rate climbs steadily and smoothly. The standard deviation is tiny. In contrast, GGPO with the same reward shows wild swings, high variance, slower convergence. Why? Because it's constrained by identical states. It can't group effectively. SRGPO, by contrast, leverages randomness intelligently, and the more steps you can group, the better the estimate. In fact, increasing the group size doesn't cost more computation, a major advantage over state-based methods. Even more impressively, when trained on out-of-domain scenes, new environments never seen during training, SRGPO still outperforms all others. Its generalization capability is top tier. This suggests the model learns principles, not just patterns. So what's the takeaway? SeeNav-Agent isn't just another tweak. It's a complete rethinking of how we build vision-language navigation agents. By combining dual-view visual prompts with bounding boxes, navigation lines, agent markers, action projections, and view alignment, it dramatically reduces hallucinations and improves spatial understanding, all in a zero-shot setting. And through SRGPO, it unlocks dense, efficient, state-independent reward signals that make reinforcement learning work in practice, not just in theory. The result? A navigation agent that sees more clearly, reasons more accurately, and plans more effectively. This work pushes the boundaries of what's possible with LVLMs, not just for navigation, but for any task where perception, reasoning, and planning must be tightly coupled. And the future? The team plans to extend SRGPO to other long-horizon tasks, like robotic manipulation or autonomous driving, wherever a state-independent reward can be defined. But for now, SeeNav-Agent stands as a powerful demonstration. When you give the AI the right visual cues and the right learning signals, it doesn't just follow instructions, it understands the world. And that's the future of embodied AI.